Welcome back, welcome back, my dear students. Welcome back. Yeah, we are live now. Are you all able to hear me, see me? Very happy. Good morning, good afternoon, good night, everyone. You're all welcome, beta. You're all welcome. Very happy. Good evening to all of you. Very happy. Good evening, beta. How are you all? कैसे हो भाई आप सभी लोग? Are you all able to hear me, see me? Audio, video, crystal clear to all of you. Very happy. Good evening, beta. Very happy. Good evening. HR आयुष प्रशांत सुस्मित नैंडी श्यान मुखर्जी एवरीवन बेटा स्वागत है आप सभी का यू आर ऑल वेलकम सो नाउ वी आर इन लेक्चर नंबर 7 still Arrhenius theory is going on. So once again you are all welcome. Now we are in lecture number 7 Arrhenius theory and numericals. As you all know, this has Gaurav Srivastav sir from Engineers Institute of India, best chemical engineering institute for GATE preparation for GATE 2026. I have 14 plus years of teaching experience as GATE chemical engineering educator author. I have multiple GATE top ranks like this year rank AIR 43. Okay. So without any delay, but I am going to start today's session with yesterday's homework, or you can say previous lecture number 6 homework. So you had completed this homework, beta. Please everyone tell me. ये complete कर लिया था? Everyone please confirm me, beta. I am going to discuss this homework. So completed. If completed, then very good. Then just compare your answer with my answer. Okay, beta. So I'm going to solve this immediately. So for a gas phase reaction at 400 Kelvin, the rate is represented as minus dPa by dt is equals to 3.66 Pa square, and the unit of this rate of reaction is atm per hour. Definitely this is, you can say, partial pressure upon this is time. So pressure upon time. So here asked what are the units of rate constant. If still not done, then please write unit of rate constant and then compare with my unit. Okay. So clearly here our equation is dPa by dt, and it is written as 3.66 Pa square, and my dear students, here overall unit written as atm per hour. Okay. Okay, students are still joining. So beta, I am waiting for next 30 seconds. After 30 seconds, we will start this session. Okay. We will resume this session. So till you have 30 seconds, you have to write the unit of rate constant. Okay. So फटाफट rate constant लिख दीजिए. And my dear student, new batch is already started. One more new batch is going to start soon. So if you want to enroll in this batch or in any other batch, beta, number is there on your screen. You can call on that number, or you can directly contact with me on my number. Okay. You know my number also. So any doubt, feel free to ask me. 9451707049. Okay, so new batches are already launched for offline online classes, beta. As soon as possible, I hope that you are now going to join. So now please tell me, beta. Then ATM inverse our inverse Divyansh. Okay, ATM inverse our inverse. Now just you remembered, beta, I told you how to write units by conventional method, or you can say general method. General method से unit को कैसे लिखा जाता है. Like here, what is rate constant? This is 3.66 is our rate constant. So here actually this is what? This is our rate constant. Here beta, this is our rate constant. ये यहाँ पे क्या है? ये यहाँ पे आपका rate constant है. This is our rate constant. Okay. And now we want unit of this. No need to worry here. Clearly here the pressure we are taking in ATM. So when we are going to write it, definitely 3.66 into PA square having unit of atm per hour. atm per hour. So what is the unit of? If I'm writing unit of this whole 3.66 into PA square, then it is beta atm per hour. And now if I want to write unit of just 3.66, unit of 3.66, that is our reaction rate constant here in this case. In this case, So it will be atm per hour, and again upon 1 upon unit of pa square, 1 upon unit of this pa square. And now you all know beta, pa is pressure here, so pressure unit here atm, so atm square. So absolutely correct beta, जिसने भी बोला है, that's our 1 upon hour atm, absolutely correct. So unit is, you can say atm inverse hour inverse. So this is the unit of reaction rate constant. So please everyone confirm me कि आपका भी यही आया था बेटा. Please everyone tell me beta, you also got same. वेरी गुड बेटा आयुष, वेरी गुड. श्यान मुखर्जी, क्या दास, क्या बात है बेटा, फैंटास्टिक, बहुत ही अच्छे, बहुत अच्छे, बहुत अच्छे. ओके, वेरी गुड. एंड नाउ सेकंड पार्ट बेटा, सेकंड पार्ट ऑफ दिस क्वेश्चन, प्लीज टेल मी आंसर. टेल मी आंसर फॉर सेकंड पार्ट बेटा. सेकंड पार्ट में क्या आंसर पाया आप, क्या आंसर आया आपका? जस्ट राइट इन योर कमेंट सेक्शन, जस्ट राइट आंसर इन कमेंट सेक्शन बेटा. Unable to solve? No, 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 beta. This time, my dear students, I am asking about the value of rate constant. Okay, the value of rate constant, not unit. I want the value of rate constant. What is the value of the rate constant for this reaction? Okay, if reaction is represented as this one or reaction is represented as this one. Okay, 120.13 liter per mole per hour. Okay, just I want numerical value beta. 120.12. That means two students getting same answer 120.13. Other beta, please everyone tell me. आप लोग का क्या आया? Everyone please tell me your answer beta. Because the right answer is 120.13 liter per mole per hour. Absolutely correct beta Divyansh. And HR. Beta, what's your name HR? Clear beta? कौन सा बच्चा इसे नहीं लगा पाया? Please write R in comment section. Waiting for your comments beta. Everyone please tell me. Those who are unable to solve, please tell me in comment section. Still waiting for your comments, my dear students. I want comment from each and every student. If unable to solve, then please write R in comment section beta. If forget to solve, still you have to write R in comment section. Sir, I was unwell past 2 days. ओके बेटा, नो प्रॉब्लम, अभी ध्यान रखेंगे अपना अच्छे से. मैं नहीं लगाया पाया सर अच्छे से, कोई बात नहीं बेटा. श्यान मुखर्जी 18-19. ओके, नो प्रॉब्लम, नो प्रॉब्लम बेटा. क्या दास, डोंट वरी, डोंट वरी, आई एम गोइंग टू सॉल्व. जस्ट फोकस हियर. अगर नहीं लगा पाए तो देखो आराम से डिटेल सॉल्यूशन हम धीरे धीरे सॉल्व करते हैं. आई एम गोइंग टू सॉल्व दिस क्वेश्चन स्टेप बाय स्टेप. So this time, my dear students, we want to write this dpa by dt is equals to 3.66 pa square. This is our equation already given with our problem, and this time we want to write this expression as first number C, 18th number, minus R is equals to minus RA is equals to minus 1 by V dNA by dt, and that becomes equals to KCA square. And this time, my dear students, here the unit for this 18th number is mole per liter per hour. Mole per liter per hour. So this is our unit beta. 18th number. First the 18th number followed by 19th number. Now what to do, how to solve it? Very easy here. Very easy. Clearly mentioned in your question, gas phase reaction. Gas phase reaction. So my dear students, here you have to take one assumption, and definitely this assumption you can also take in a GATE examination. For any gaseous phase, if nothing mentioned like non-ideality, then from your side you can assume that gaseous mixture or pure gas is an ideal gas, Okay, so we are assuming here that this gas phase is an ideal gas because no non-ideal data is present. That means ideal gas case. Okay, so ideal gas, and this gas is available at some temperature 400 Kelvin. Okay, now you all know for ideal gas equation, you know, for ideal gas, you can write PV equals to nRT, ideal gas equation, PV equals to nRT. Now, further, if you want to write this equation here, so further you can write like P equals to N by VRT. N by V. What is this? Mole per unit volume. This is concentration. Mole per unit volume. Concentration, or you can say molar density. This is concentration, or you can say molar density. So here we can write pressure is equals to concentration CRT. Now, if we are writing just for any component A, for component A, then my dear student, this total pressure now substituted by partial pressure. So here now you have to write PA, and now here instead of total concentration, concentration of A, so you can write CART. That means beta we can write in place of PA CART. So now if we are going to assume this as our equation number 1 and this as our equation number 2. So clearly now you are able to put the value of PA from equation number 2 to equation number 1. Now see what will you get? Just बस इसे आपको put करना है. Just you have to put, my dear students. So it will come minus by equation 2. Equation 1 becomes, अभी देखो equation 1 क्या हो जाएगा? What is going to happen with equation number 1? So here it is minus dpa by dt. It is minus dpa by dt. So I can write minus d by dt, and in place of pa beta I can write cart, and that becomes equals to 3.66, and here pa square was there, so I can write here cart whole square. Please tell me everyone, but till now everything is crystal clear. Tell me, beta, everyone. Any doubts till now? Or we can proceed step by step. Please tell me, beta. Any doubt, or we can proceed? Any doubts, my dear students? No doubts. Confirm? Okay. Okay, very good, very good. Crystal clear. Then great. Now, you know, beta, R is universal gas constant. It is not going to depend upon time. Temperature is also clearly given that the gas phase reaction is going to happen at some 400 Kelvin temperature. That means isothermal condition. And for this temperature, you are going to change conversion. You are going to do this conversion. आप इस temperature पे इस conversion को करने जा रहे हो. So clearly I can write here beta minus RT into dCA by dt. Okay, and that becomes equals to beta 3.66 into CA, or first you can write this RT square, 3.66 into RT square into CA square. Now see RT RT, both side RT. So this RT will be cancelled, this is square, and now what will we get beta? You can write further as minus dCA by dt, and that becomes equals to 3.66 RT into CA square. Now conversion completed. The first step of conversion completed. Now clearly you can compare this equation with this equation. See, KCA square RA. And what is this? This is minus D Na by V by dt, and a mole per unit volume, my dear students. Further you can write as minus dCA by dt. That means left hand side conversion done, right hand side also done, and here we are getting this whole in place of reaction rate constant. So definitely it is going to give us the value of, this will give you the value of new reaction rate constant. This is what? This is rate constant. दिस इज रेट कांस्टेंट. अब ये क्या हो गया है? ये आपका रेट कांस्टेंट हो गया. नाउ यू कैन एज्यूम दिस रेट कांस्टेंट as suppose I am writing like k dash, or because previously we had not written anything, so just write like k, reaction rate constant k. This is now your k. By comparison, this is our k. But still the numerical value is not there. Numerical value is not there. So now how to get numerical value? It's very very easy, beta. Just focus. Just focus. Now this time the overall unit, when you are writing in this term, so it is asking in this mole per liter per hour. So here you have to write, beta, the unit is mole per liter per hour. This time you want a unit in this mole per liter per hour. Okay. So when you are writing in this unit, and this is your rate expression. So my dear student, this is dCA by dt. If you are writing this as kCA square, and this time the unit is mole per liter per hour, so just you have to check what should be the unit of this k this time. What should be unit of k, reaction rate constant this time? So here beta, unit of k, please everyone write unit of k. सभी लोग यूनिट ऑफ के लिखोगे. यहाँ पे यूनिट ऑफ के क्या आ रहा है? एंड आफ्टर राइटिंग जस्ट राइट डन इन कमेंट सेक्शन. प्लीज एवरीवन राइट यूनिट ऑफ के, and after writing please write done in comment section, beta, everyone. Right, beta? Just after writing please write done in comment section. I'm waiting for your comments. Done. Okay, very good, fantastic, fantastic, mind blowing, super, super. So just you have to use conventional method here. KCA square having unit of mole per liter per hour, so the unit of k will be mole per liter per hour upon Ca square unit, and Ca square is mole per liter. So clearly liter cancelled, this will be cancelled by this one. So the unit that we are getting here, finally it is a liter per hour per mole, or you can say liter per mole per hour. Please tell me, is it same to same that you are getting? क्या आपको भी यही मिला है बेटा? So liter per mole per hour. Very good, beta. Shushmit Nandi, absolutely correct. Absolutely correct. So you're also getting same to same unit. Okay, very good. That means, beta, this time our k that you got, just you got the k. So this time the k is 3.66. But wait, this is not just 3.66. You know the unit of 3.66 is 1 upon atm per hour, and into R into T. Now overall unit of K we want in liter per mole per hour. Liter per mole per hour. Okay, fantastic, mind blowing, super. Now you have to set, like here this temperature will be in Kelvin. So now you have to check that from, you know the value of R, everyone I hope no, general value of R, that is 8.31451 kilopascal meter cube per kilomole per Kelvin. Hmm? So here in which unit you are going to put this R, so that after cutting 1 upon atm, 1 upon hour into Kelvin into this R unit. ओवरऑल आफ्टर कटिंग यू हैव टू गेट लीटर पर मोल पर आवर। आपको ये लेना है। आप आर की एक ऐसी यूनिट को यहाँ रखो जिससे कट पिट कर ये टेम्परेचर की यूनिट और ये रिएक्शन रेट कांस्टेंट जो पुरानी वाली थी इसकी यूनिट से कट पिट के एट द एंड यहाँ मिले। सो कैसे निकालोगे? नाउ फर्स्ट यू हैव टू चेक दैट इन विच यूनिट यू नीड द वैल्यू ऑफ आर। The first step here you have to check in which unit you need the value of R. So very easy beta. R unit. See how I am defining the unit of R here. In which unit I want this R. So it will be, this is overall unit, this is complete unit. So it is liter per mole per hour. Now this whole, if you want R unit, so 3.66 unit you are going to write on right hand side. So it will be here ATM into hour. Here denominator, so right hand side it is in numerator. Kelvin here numerator, so here it will be in denominator. Now just check it beta, just check it. Hour cancelled, hour cancelled. That means this time we want this unit, the value of r, we want the unit for value of r is atm liter and per mole per Kelvin. I hope everyone is crystal clear. Okay. Now, so how to do conversion? We already discussed this conversion in process calculation, but still, if you have not started class resolution, then don't worry. No need to worry. Just see here. Here the conversion factor. You want to convert this kilopascal into atm. Then you want to convert this meter cube into liter. Then the next one you have to convert this kilomole into mole. Kelvin to Kelvin, no conversion required. See, from this side you want to get this one. So write just here 1 1 1. You know 1 kilopascal is equals to how much atm? How to write? You know 1 atm is equals to, everyone know that 1 atm, 1 atmospheric pressure is equals to 101.325 kilopascal. So 1 kilopascal will be equivalent to 1 upon 101.325 atmospheric pressure. 1 meter cube is equals to 1000 liter. 1 kilomole is equals to 1000 mole. Now, how to get final value? So just see R is equals to, first write numerical value that already you have 8.31451. Now multiplied with, in place of kilopascal, my dear students, you can write 1 upon 101.325 atm. In place of meter cube beta, you can write 1000 liter, and whole upon, in place of this kilomole, my dear students, you can write 1000 mole. In place of Kelvin, no conversion required. Now just you have to separate numerical values from units. So it will come 8.31451, and this 1000 cancelled, and this whole upon just 101.325, and now it is in atm liter per mole per Kelvin. Now please tell me beta, just divide this and tell me क्या मिल रहा है? So 8.31451 divided by 101.325. It's 0.082057. So up to 5 decimal place, I am writing like 0.08206. Fantastic, mind blowing, super. I hope each and every student is crystal clear, beta. I hope बहुत जल्दी जल्दी नहीं बता दिया है. Speed is normal one because very easy topic. So no one to invest extra time, like very slow करते हुए इसे करें. So I hope you are able to understand. This speed is okay to all of you. So please everyone tell me beta, is it crystal clear? Can we proceed beta? Can we proceed, my dear students? Everyone. Can we proceed? No doubts. Crystal clear. Sir, in problem 14, why K2CA half is unitless? Why K2CA half? Bhogi Sai Kumar. Beta Sai Kumar, don't worry, I will take your doubt after this problem. Okay? इस प्रॉब्लम के बाद आपका हम डाउट ले लेंगे. Speed is okay, sir. That's great, beta. That's great because syllabus is very very large, and I am going to deal this CRE in a detailed manner. Okay, that means after that, blindly you can say that definitely I am able to solve all questions that will be asked in gate 2026. You know, this year how much marks asked from CRE? क्या आपको ये पता है? Please tell me in comment section. Direct from CRE, how much marks asked this year? Hello, yes, yes. Sushmit Nandi, Devyans, Ayush, Kiyadas, Bhogi Sai Kumar, don't worry, but I will tell you. I will tell you orally if you want, then beta that is unitless because one is there along with that part. Okay, that's why we took that also as unitless because complete unit part is in numerator. Sir, for gaseous reaction, can we write Na by V is equals to Ca? Yeah, beta. For gases as well as for liquid. But one thing you must become sure that if gas is there and reaction is going on, then whenever you are going to write V, then V may be a function of conversion if expansion coefficient epsilon is not equal to 0. That is V is equals to V naught 1 plus epsilon XA. And for this time, please forget these all things. You will see these things in detailed manner. ठीक है, वो डिटेल्ड मैनर में आपको दिखाएंगे, तो अभी चिंता मत करो. स्टिल यू आर इन जस्ट स्टार्टिंग फेज ऑफ सीआरई. Okay, approx 15 marks. Don't know, beta. Directly 14 marks. Direct means total direct from CRE, 14 marks. After that, CRE plus PC, one mixed question, 2 marks. CRE plus IPC, one mixed question, 2 marks. So directly and little bit other subject you are taking 18 marks. And if you are forgetting other subjects, and a few more questions are there in which knowledge of CRE is required. I'm not taking simple balance type in which just you are able to solve with the help of process calculation. I'm taking just in which a CRE is required, like from kinetics, heterogeneous reaction. Many questions are there, not a single question. Many questions are there. Non-ideality in reactors, many questions are there. And if you want to know non-ideality or heterogeneous and these all things, then basic is required for each and everything, each and every question. Okay, each and every chapter is each and every future chapters. Definitely, you will be able to clear with a 0% darkness if your fundamentals are strong. Okay, yes sir. अभी मुझे पता चला सर. Yeah, so beta see 14 number, 14 marks just from CRE. Oh my god, 14 marks directly. This is directly. I will show you. I will show that paper in my next lecture. वो सारे क्वेश्चन हम लगा देंगे एक स्लाइड में, फटाफट आपको दिखाएं. I will show all questions that asked in gate 2025. Okay, अभी उसकी स्लाइड नहीं बनाई, बट आपको बना के हम दिखा देंगे. ओके, वेरी गुड. सो कहाँ तक आ गए? हाँ, सो स्टिल आर वैल्यू एवरीवन क्रिस्टल क्लियर माय डियर स्टूडेंट्स? आर की वैल्यू तक किसी का कोई डाउट नहीं है? नॉट अ सिंगल परसेंट डार्कनेस इज देयर ना? एवरीवन क्रिस्टल क्लियर? Okay, very good. So beta please solve this and tell me value. I'm coming in just 30 seconds. Just I want some drinking water. I'm coming, don't worry. Okay, back. Okay, so tell me beta, Everyone now getting same answer 120.13 आ गया क्या आपका 120.19 very good very good no problem fantastic super okay so now just you have to put so the value of k this time will be 3.66 multiplied already we checked by cutting units. So the R value directly here you have to write if 0.082006 temperature was 400 Kelvin. So after solving this beta you will get 120.19 and unit already we checked that the unit will come for this case liter per mole per hour. Liter per mole per hour. Okay. So just tell me beta, is it crystal clear? Can we proceed? Can we proceed my dear students? नेक्स्ट प्रॉब्लम की तरफ बढ़ा जाए. Okay, fantastic, mind blowing, super. So now see problem number 19. Same to same, this time also same to same, but this time we want in mole per meter cube per second. Little difference is there. So mole per meter cube per second, mole per meter cube per second. Okay, no problem. So this time we want mole per meter cube per second. That means when you will get the value of k this time, so mole per meter cube per second, volume in meter cube instead of liter. So definitely after cutting these all things, here instead of liter you will get meter cube, and mole will remain mole, but hour will be converted into second. So very easy here, very easy. No need to do again complete thing from the start. Step number one. Directly you can do this conversion from this value of k. So are you able to do this? Please do this for me and tell me answer. Yeah. Please everyone do this for me. Okay. फटाफट इसे करोगे and then please tell me answer बेटा. Everyone. Please do this for me and tell me answer. Tell me answer everyone. And it will be great if I'm going to give you just 2 minute timer. Okay, so 2 minute का एक timer ले लो. Just take this 2 minute timer ताकि सब में पता चलता रहे जाए. Okay, time is started. So max time you can take 2 minutes and just tell me answer. Just do this conversion for me. Conversion will hardly take your 15 seconds. Yeah. Okay. So I'm not giving complete 2 minutes. Okay. Just when I got answer from you, no, but Ayush, this is not correct. But Ayush, your answer is not correct. But you have to convert liter to meter cube. 1000 liter is equals to 1 meter cube. So 1 liter is equals to 1 upon 1000. So value will be very less this time. Okay, hour is in denominator. 1 hour is equals to 3600 second. Are you getting my words, but Ayush? Divyansh, I think your answer is correct, but we have to check. I will check. I will check it. But still, Ayush is also getting same answer now. That means both are correct. Both are correct. Very good, very good. But still 30 seconds left. Please, everyone, tell me answer. Come on, everyone. Just write your answer in comment section, beta. Still waiting. Last 37 seconds. Last 15 seconds. Okay, so time up. Time up. Time up. So Devarsh Agnihotri, Susmit Nandi, Bogi Sai Kumar 0.00003. Better, but you have to give into 10 raised to power minus 5. It will be more better. Okay. Very good, very good. Almost every student's now getting same answer. Fantastic, fantastic. Now, see if you're still unable to do this conversion, no need to worry. No need to worry. Just focus here. Just do these fundamental steps. So liter you want to convert in meter cube. See, liter you want to convert in meter cube, and mole you want to convert in mole. No conversion required. Hour you want to convert into second. So just write 1 here. Basic rule. So 1 liter, 1000 liter is equals to 1 meter cube. So 1 liter will equals to 1/1000 meter cube. 1 hour is equals to 60 minutes. Every minute 60 seconds. So 16 to 60, 3600 seconds. Okay. Now, how to solve here? How to solve? So again, you have to do same to same technique. Take this, write this numerical value first, so 120.19. Now multiplied with, in place of liter, you have to write 1/1000 meter cube whole upon mole into 3600 second. Okay, so I'm not going to do this conversion because everyone getting same answer. So I'm writing same to same, 3.33 into 10 raised to power minus 5 meter cube per mole per second. Okay, is it crystal clear to all of you, beta? So this is your आंसर नंबर 19. ये आपका आंसर नंबर 19 हो गया. ओके, सो एवरीवन क्रिस्टल क्लियर बेटा? बोलो सभी का आ गया? कैन वी प्रोसीड? कैन वी प्रोसीड माय डियर स्टूडेंट्स? क्या हम आगे बढ़ सकते हैं? क्रिस्टल क्लियर सर. ओके ओके, वेरी गुड बेटा. नाउ a few more analysis I want to do for activation energy here. Okay. Now just I want one answer from your side here. Okay, this problem completed. Now next topic, that is discussion about activation energy. Just you had seen few things about activation energy. Just I want to check your knowledge again. So this is your activation energy. Okay, and I am taking two different cases, and both cases I am taking here for isothermal condition. So please you can write with isothermal condition. Okay, in first case, my dear students, the value of activation energy is given something like just write high value, ea is high, and in the second case the value of ea is less, lower value. Now my question is, ea large, ea small, can you tell me which reaction is faster one? Are you able to tell इस दोनों में से ज्यादा तेज कौन सा रिएक्शन होगा? Which reaction is faster one? Just tell me fast reaction, slow reaction. First one, second one. Which one is fast? Which one is slow? इसमें से फास्ट रिएक्शन कौन सी है बेटा और स्लो रिएक्शन कौन सी है? प्लीज एवरीवन टेल मी. Which one is fast reaction? I want comment from each and every student यार. सभी लोग कमेंट किया करो. सभी लोग कमेंट किया करो. नाउ प्लीज टेल मी बेटा, which one is fast? Second is fast sir. Lower one is faster. Very good Shyam Mukherjee, Susmit Nandi. Second is fast. Everyone is correct. Everyone is correct here. So low activation energy is going to represent you faster reaction. Faster reaction. Because the reaction path is less in comparison to this one. So here this will be slower reaction. This will be slow reaction. चलो बहुत अच्छी बात है. Very good, fantastic. Now, few more thing I want to discuss here. Few more thing I want to discuss. First, I want to show you few equations from thermodynamics. Do you know one equation is there, Clausius and Clapeyron equation, and one more equation, Van 't Hoff equation. क्या इनका नाम सुना है आपने बेटा? Please tell me everyone. You will see details of these equations again in thermodynamic subject, so no need to worry. Here just I want to tell you a small story about these equations. So just tell me बेटा, ये नाम आपने सुना है? Anyone? Clausius and Clapeyron equation and Van 't Hoff equation. Please everyone tell me बेटा. See, but a Clapeyron equation is different one. Clausius and Clapeyron is different one. Okay. So here I am asking about Clausius and Clapeyron equation. Okay. And then I am asking about Van 't Hoff equation. Van 't Hoff equation. इनके नाम सुने हैं आपने? Just tell me. ये देखा तो होगा ना कभी थर्मोडायनेमिक इंपॉर्टेंट इक्वेशंस. प्लीज टेल मी बेटा एवरीवन. फटाफट बोला करो यार कमेंट सेक्शन में. सुना है सर. क्लासेंस कैपरॉन सुना है. वेंट ऑफ नहीं सुना है. सुस्मित नंदी डोंट नो वेंट ऑफ इक्वेशन. सुस्मित नंदी बेटा. ओके. You will see details of these equations again in thermodynamic subject. Here just I want to show few things about these equations. So Clausius and Clapeyron equation is d ln p star d ln p star upon dt. Similarly, in Van 't Hoff equation, it is d ln k d ln of ke by dt is equals to. So in left hand side beta, you can see p star is substituted by ke. What is ke? I will tell you, don't worry. And it becomes equal to delta h web t, delta h web. This t represents this delta h web is a function of temperature. This T represents delta H web is a function of temperature. Okay. So delta H web upon RT square. And here if you are going to write, then this instead of this delta H web, you have to write delta H reaction. And beta C. Heat of reaction is also a function of temperature. And I already show you the equation, developed equation in my process calculation lecture. So if you had seen, if you had completed that lecture, then that's great for you. If you're still not completed, please try to complete it as soon as possible. Okay. So this is heat of reaction and whole upon R T square. For some general ranges of to solve question, mostly with your problem they are giving like heat of reaction is constant here. It doesn't mean that heat of reaction is always constant. It is a function of temperature. ये function होता है किसका? Temperature का. Okay. So the first one is Clausius and Clapeyron equation. Here P star is vapor pressure and delta H vap is heat of vaporization. So what is P star? P star here is vapor pressure. You know well about this, already discussed in process calculation. Okay, but here इसका जरूरत नहीं पड़ेगा. We don't need it. Okay, just here you need for some conclusion about Arrhenius, given conclusion given by Arrhenius. Okay, for that purpose just you are seeing this Clausius and Clapeyron equation and Van 't Hoff equation. Their application you will see, the Clausius and Clapeyron equation application you will see only in thermodynamic subject. And this delta H vap, this is what? This is enthalpy of vaporization. This is enthalpy of vaporization. Similarly, my dear students, here the K that you are seeing, this is equilibrium reaction rate constant. This is equilibrium reaction rate constant. Sir, what is this, sir? Don't worry. See, suppose a typical reaction A that is going to give you R. So here this is forward reaction rate constant Kf and this is backward reaction rate constant Kb. You know Already we discussed in the starting lectures of CRE. Forward activation energy, backward activation energy, both are different if exo or endothermic reaction is there. If reaction is neutral one, neither heat is evolved nor heat is absorbed during chemical reaction, then for that case forward and backward both will remain same, and that is a very 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 rare thing that you are talking about. Okay, so A is forming R, so definitely Kf is not equal to Kb here. Kf and Kb mostly different. Okay, so if you are writing this Kf forward reaction rate constant upon this backward reaction rate constant बेटा, then this is termed as बेटा इक्विलिब्रियम रिएक्शन रेट कांस्टेंट के, ये और कुछ नहीं, यही आपका के है, दिस इज योर के. Okay, is it crystal clear to all of you beta? Please everyone tell me. You will again see details about this K when I will discuss the kinetics of reversible reaction, so don't worry. This time just I want to show you one thing about Arrhenius. So just I want to give this equations here. Okay, is it crystal clear? मजा आया था पीसी लेक्चर में, क्लास में? वेरी गुड बेटा. ओके, थैंक यू बेटा श्याम मुखर्जी. Want of equilibrium constant and heat of reaction correlation, या बेटा वेरी गुड, एब्सोल्युटली करेक्ट. याद नहीं है सर शायद, कोई बात नहीं, सुना है ना, अभी याद कर लो ना, अभी याद कर लो. थर्मोडायनेमिक्स का इंतजार मत करो, डोंट प्लीज डोंट वेट फॉर थर्मोडायनेमिक्स. रिमेंबर इट इमीडिएटली. ओके, रिमेंबर इट इमीडिएटली. डन, नो प्रॉब्लम एट ऑल. Very good, fantastic. Now wind up equation and classes and Clapeyron equation, and this equilibrium reaction rate constant K, clearly you can see K is a function of temperature. This K is a function of temperature. This K is a function of temperature. ये K क्या होता है बेटा? ये function होता है temperature का. And soon you will, when you will see the kinetics of reversible reaction, then you will also derive a few expressions regarding this. Few expressions, आप इसके लिए कुछ expressions को भी derive करोगे. Okay, and just like a typical expression if you want here, so for this reaction xae can be written as k beta 1 plus k. xae can be written as k upon 1 plus k. कैसे आया sir? How sir you got it? Don't worry, you will see its derivation in my subsequent lecture, so don't worry. Okay, and how sir you are saying k is a function of temperature? ये कैसे कह दिया सर आपने? See here, just integrate this equation, then you will get ln of K, and that becomes equals to minus delta H by RT, and one reaction rate one integration constant required, so you can write just like ln of K naught, ln of K naught. Now further solving, it can be written as ln of K upon this constant K naught, and that equals to minus delta H by RT. And further solving, my dear students, here you can write k upon this constant k naught equals to exponential of, that is e raised to power minus delta H by RT. Or you can write k, and that k becomes equals to e raised to power minus delta, sorry, it will be k naught e raised to power minus delta H by RT. Now please just see it carefully. Clearly, my dear students, if you are going to increase this t, overall negative value is there. So e raised to power negative decreases. If e raised to power negative decreases, e raised to power negative decreases, the value of this will be increases. But wait, is this sign is always negative? No. Why no? See, this delta H, you know beta, negative when the reaction is exothermic heat of reaction, and the same delta H is positive if the reaction is endothermic. So clearly this minus sign will sustain here only in case of endo one. That means this one I am writing for endo. So one beautiful conclusion you got beta. What conclusion you got? See, I'm writing again here endo, for endo reaction, for endo reaction. If you are writing Ke, so Ke will be increases when you are going to increase the temperature. Just you had seen from here. But the same thing when you are checking for exo, and which exo, clearly here K is present. So the whole thing that you are seeing here, beta, that is for reversible reaction. These all for reversible reaction. These all for reversible reaction. Okay. So for exothermic reactions, my dear students, here if you want to write and if you want to increase T, what will happen? Let me check. Let me check. This will be Ke, and this K becomes equals to K naught, and e raised to power minus, and minus will make the numerator positive. So positive upon RT. Now if T increases, oh my God, positive power decreases. Positive power decreases, that means overall value decreases. So here this is our conclusion. This is our conclusion. And definitely if a temperature you are going to change, so clearly Ke changed, and if Ke changed, then this is known as equilibrium conversion. You will see details about this equilibrium conversion soon. This I'm giving some details. Okay, some details about these all. Okay, so these all things better you can see with the help of want of equation. So I hope everyone is crystal clear till now. बोलो बेटा सभी को क्लियर है? Can we proceed? 10। ये पता नहीं क्यों स्क्रीन यार ऑफ हो जा रही है बार बार हमारी, कौन सी सेटिंग ऑन हो गई है, आई डोंट नो। ओके, क्रिस्टल क्लियर सर, वेरी गुड। सो the first one is classes and Clapeyron equation, and second one is want of equation. With the help of want of equation, you will also see this analysis of a want of equation in thermodynamic chemical equilibria chapter. How reaction rate constant, equilibrium reaction rate constant is going to vary with temperature. ये temperature के साथ कैसे vary करता है? You can take two cases, just like I am going to do the thing for activation energy. The same thing you can do for equilibrium reaction rate constant. But this time I'm not going to show you. I will show you later. I will show you later. कैसे इसको निकालते हैं, I will show you later. But if you want to write, so you can write in this way, like ln of Ke2 upon Ke1, and that will be equals to delta H by R, and here 1 by T1 minus 1 by T2. And see beta, this is not mod of delta H. This is just delta H. That means if exothermic, here negative sign will be present. If endothermic, positive will be here. Okay, so this beautiful relation is there. You can easily derive it. You can easily derive it. How, sir, we can derive it? Can you tell me? I will tell you just in this lecture in similar manner, because I am going to derive for activation energy and reaction rate constant. Okay, reaction rate constant and activation energy. Just you can write this for two cases, like just here you can see this equation. Okay, so for first one, this is ln Ke delta H upon RT1, and then again ln Ke delta H by RT2. And definitely for this relation, delta H you have to assume, here one assumption is there, that delta H is not a function of temperature. Here you are assuming it. यहाँ आप इसको assume करके चल रहे हो, ये बात ध्यान रखना. That delta is not a function of temperature. If this is a function of temperature, then this equation is not correct. In that case, 2 delta H will be present in your equation. Okay. So till now you had seen classes and Clapeyron equation. You will see details about this equation in thermodynamics and want of equation. Again, I am saying details नहीं बताते बताते कितना डिटेल बताते जा रहे हैं ना. ओके, अब इसके बारे में अभी बात नहीं करेंगे, बाद में बात करेंगे. नाउ आई एम नॉट गोइंग टू टॉक अबाउट वांट ऑफ इक्वेशन. ओके, सो जस्ट सी. So this is your Clapeyron equation. Here the main mother equation. Now how want of equation come from classes and Clapeyron equation? Just inspired and ignite, inspired and ignite. You know lots of subjects name like mass transfer operation, like heat transfer operation, like fluid mechanics, momentum transfer, heat transfer, mass transfer. In all of these subjects beta, the mean rate of transfer everywhere you can see, my dear students, is proportional to driving force upon resistance. Analogous nature. Resistance is equals to driving force upon resistance. Everywhere you can see this. Okay, that rate becomes equals to driving force upon resistance. So what is this? This is analogous nature. This is what? This is analogous nature. इन सारे सब्जेक्ट का क्या है बेटा? एनालॉगस नेचर है. द सेम थिंग हियर ऑल्सो फील्ड बाय Wenthoff. So he told that see classes and clapron, I am inspired from your equation and now I am giving the similar equation. But wait, you are giving equation in which you are going to calculate vapor pressure as a function of temperature. That means when you are changing temperature, vapor pressure will be increases or decreases. You have to check from this equation. When you are going to increase temperature, what will happen with vapor pressure? It will increase. And how much increase or decrease, if you want to check, you can check with the help of this equation. And here also assumption taken by Clausius, because in Clapeyron equation this assumption is not present. So in Clausius equation, this is an assumption that enthalpy of vaporization, that is just like lambda. This is lambda. Okay, so this is not a function of temperature. इन हिज डिटेल्ड स्टडी जब आप ऐसे करते हो मान लेते हो कि यह टेम्परेचर का फंक्शन ये नहीं है, बट रियलिटी में इट इज अ फंक्शन ऑफ टेम्परेचर. इट इज अ फंक्शन ऑफ टेम्परेचर. अ डोम लाइक कर्व you can see there. So this is latent heat here, this is latent heat at some other pressure, this is latent heat at some other pressure, this is latent heat at some other pressure. So if we are in the close range, then you can say latent heat is nearly change is negligible. And details you will see in thermodynamics subject. Okay, here just I want to show how Arrhenius equation came to the picture. So classes and Clapeyron equation, want half, inspire, ignite. Now same thing, inspire and ignite Arrhenius. And Arrhenius gives his equation. Arrhenius equation. Arrhenius equation. So what is Arrhenius equation, my dear students? How it is come? कैसे आया ये Arrhenius equation? Inspired and ignite. देखा किया, ये तो यहाँ भी सही हो रहा है. So now, see, Arrhenius told that, okay, Wenthoff sir, you told me that A is forming R. This is forward reaction rate constant. This is backward reaction rate constant. Okay, fantastic. Super. So, if this is correct, then I can also write your equation just by considering one direction. And I can write for just one direction. And I can do the other direction again in similar manner. That means the same calculation I am going to calculate in two steps. How, sir? Now, see, I am going to show you how. Don't worry. So, by want half, I am taking want half equation and I am showing you Arrhenius work. Okay, so by want half equation. Just you had seen want half equation, that was Ke, and Ke becomes equals to some constant, integration constant K naught into E raised to power minus delta H by RT. Now, see this diagram beta. Already you had seen this diagram many times. One more time, just focus here. This time I'm writing energy, and this is energy, and this side I'm writing direction coordinate. And this graph is suppose like this, like this. Okay, so clearly this is your reactant and this is your product. A is forming R. Definitely forward activation energy is this one. If you are writing, this is what? This is your forward activation energy, EF. And if you are going from this to this direction, then this is your backward activation energy, EB. And clearly, my dear students, this is what? This is heat of reaction. This is delta H. I can write this delta H as EF minus EB. Is it correct बेटा? Please everyone tell me. देखो ये फिर से स्क्रीन ऑफ हो गई है। ये कल तक नहीं होता था, ये कुछ सेटिंग अंदर से पता नहीं क्या हो गया, स्क्रीन ऑफ हो जा रही बार बार, इसलिए हाथ में लेना पड़ रहा है। नाउ प्लीज टेल मी बेटा, आर यू एबल टू अंडरस्टैंड? प्लीज एवरीवन टेल मी बेटा, ये समझ में आ रहा? ई एफ माइनस ई बी, हाउ आई एम राइटिंग दिस, हाउ आई एम राइटिंग दिस, प्लीज एवरीवन टेल मी। कैन वी राइट बेटा? नो डाउट्स? यार कमेंट नहीं आ रहे आपके यार। बैटरी सर्वर मोड, ओह या, एब्सोल्युटली करेक्ट दिव्यांश, क्या बात यार। हमने कल रात में ही ऑन किया था, मेरा चार्जर रात में टूट गया था। यस, ये बैटरी सर्वर मोड इज ऑन। ऑफ कर दिया, क्या बात है, थैंक यू थैंक यू थैंक यू। ऑफ कर दिया यार, क्या बात है। आईटी वाले, केमिकल वाले इज नाउ आईटी वाले टू। फैंटेस्टिक फैंटेस्टिक बेटा, थैंक यू दिव्यांश। कल रात में क्या वो ना 4:30 पे चार्जर को मंगाना पड़ा, मैं रात में कुछ काम करे तो बस मोबाइल ऑफ होने वाला था, चार्जर लगाया, बस चार्जर का पिन टूट गया। थैंक यू, अब नहीं होगा, अब ऑफ नहीं होगा। बैटरी सेवर मोड ऑन था या, जैसे आपने बोला हमें याद हो आ गया। सो ये सभी को क्लियर है? यू कैन राइट ई डेल्टा एच इज इक्वल टू एफ माइनस ई वी। सो नाउ सी आई एम गोइंग टू डू सम एनालिसिस माय डियर स्टूडेंट्स। फर्दर this equation can be written as k can be written as kf by kb, and that becomes equals to k naught and e raised to power minus of e f minus e b by rt. I hope each and every student is crystal clear. So definitely you are able to write this equation in this manner. Okay, now if I'm going to take log both side, then what will we get? Ln of kf by kb, that equals to ln of this k naught, and ln of e, that means just minus ef minus eb and whole upon rt. Fantastic. Now left hand side, my dear students, you can write like ln of kf minus ln of kb, and in right hand side ln of k naught is a constant here, so that constant I am writing like ln of a plus ln of b. Any problem? No problem, this is same your ln of k naught, constant, a constant. Okay, a constant, and minus ef by rt, and the second one minus ef by rt, and minus minus will make it plus, so I am writing like minus of eb by rt. Now the same analysis done by Arrhenius, and now told please use only forward alone. This is for forward, this is for forward, and this is for forward. And then he separated these three terms, this one, this one, and this one. Now after separating, you can write these equations as ln of kf, and that equals to, by his experiments he got this result, so ln of a minus ef by rt. Similarly he got for backward reaction rate constant kb, and that is ln of b and minus e b by rt. So now he told that that means you can use this equation also if the reaction is unidirectional. If the reaction is unidirectional, still you are able to use this equation. And his conclusion, he gives that please see, I am writing just reaction rate constant instead of equilibrium reaction rate constant, and now I am writing this ln of just some my exponential factor, pre-exponential factor minus here I am writing just activation energy for that respective path upon RT. Further, if you want to write, you can write like ln of k by k naught equals to, don't worry, this k naught, that k naught is not same, both are different. Okay, this time again I'm using k naught, so if you are confusing then use here k naught dash, k naught dash, k naught dash, अगर आपको लग रहा है ये क्या हो गया. Okay, so ln of k by k naught is equals to e a by rt. Further moving, you can write this equation as k by k naught is equals to exponential of minus e a by rt. Okay. Further moving, you can write like k is equals to k naught e raised to power minus e a by rt. And my dear students, this is your final form of standard form of Arrhenius equation. So this is what? This is Arrhenius equation. Arrhenius equation. So I hope that everyone is crystal clear what is Arrhenius equation, how Arrhenius developed his equation. Please everyone tell me बेटा. बोलो सभी को याद हो गया, समझ गए? Can we proceed my dear students? No doubts everyone? Waiting for your comments बेटा. सभी लोग फटाफट बताते रहा करो, फटाफट. Don't delay in comments. Just like offline class, I want interaction from your side here. Okay, I want same interaction like offline class. सभी लोग कमेंट करो बेटा. I want comment from every student. क्या बात, फैंटास्टिक, सुपर, किसी को डाउट नहीं है. ओके, फैंटास्टिक. नाउ गर्मी में दिमाग दुख रहा है सर. शियान मुखर्जी बेटा, डोंट टाइप इरेलीवेंट मैसेजेस. इरेलीवेंट मैसेज में दिमाग नहीं लगाने का, जस्ट टॉपिक से रिलेटेड बातें करने का. सर ln k naught is ln a plus ln b. Yeah beta, here I am writing this ln k naught dash as ln a plus ln b. This one I am writing like ln of a plus ln of b. Just doing analysis in order to get Arrhenius equation. Okay, HR 1 2 3. HR, is it crystal clear beta? Can we proceed? Okay sir, crystal clear sir. Okay, now so this is your Arrhenius equation. Fantastic, mind blowing, super. You need to remember this, very easy equation to remember. बहुत ही आसानी से आप इसे याद कर सकते हो. Very easy to remember. Now in your examination they can ask you like here also you can see this k, that is reaction rate constant, is a function of temperature. From this equation clearly you are getting one beautiful conclusion that this k is a function of temperature. Now suppose in your examination someone asks you that if we are going to change temperature, what will happen with reaction rate constant, what should be the value of reaction rate constant now, new value of reaction rate constant. Don't worry, very easily you can derive one more equation in similar manner, just as you had seen in case of one half equation, how equilibrium reaction rate constant is going to vary along with temperature. But in that case delta H can be positive, can be negative. Here my dear students, this EA always positive. This EA, in this case my dear student, this EA एक्टिवेशन एनर्जी वैल्यू, दिस इज ऑलवेज पॉजिटिव. ये हमेशा पॉजिटिव होगा. दिस इज ऑलवेज पॉजिटिव. delta H may positive, may negative. Delta H was positive when equation was endothermic. Delta H was negative when reaction is exothermic. So I hope each and every student is crystal clear. Okay. Now, if EA is always positive, then what is going to happen with K when we are going to increase temperature? Let me check here. Let me check. Let me check. Everyone, please just focus here. Temperature increases. Denominator increases for given value of EA. Negative sign decreases. What does it mean? See, negative sign, suppose one time 10 raised to power minus 3, and now negative sign decreases to 10 raised to power minus 1. So initially this was 0.001, just a typical example I am sharing with you, my dear students, and here this is 0.1. So clearly, my dear student, less negative sign represents higher value, high negative sign represents lower value, but it will be opposite in case of positive sign. So high positive power will give you high value, less positive power will give you less value. But here this is not positive, this is negative power. See, e raised to power minus, e raised to power minus, okay, 2.7 something value of e. So e raised to power this minus sign. So if increasing in denominator, definitely the overall value, if you are seeing about this overall value of ea by rt, यहाँ पे अगर आप इस पूरे की वैल्यू देखोगे इससे क्या हो रहा है, this ea by rt, then my dear student, this is going to decrease. And if negative power is going to decrease, then what will happen here, my dear students, with this full value? In पूरे के साथ क्या होगा? This is going to increase. And if this is going to increase, this is also going to increase. So beautiful conclusion you got here, yeah. What is our conclusion? Above analysis conclusion is every time, even if you are seeing for forward reaction or backward reaction, this is not Ke. Ke may increase, may decrease when you are increasing temperature. It will strongly depend upon exothermic or endothermic. When you had seen about this Ke, see beta, this Ke, that is the equilibrium reaction rate constant, it may increase, it may decrease by increasing temperature. By increasing temperature, it may increase, it may increase, it may decrease. So it is strongly dependent upon the reaction is endothermic or your given reaction is exothermic. But this time, no need to worry. Even if reaction is reversible, you are seeing only one directional. What is going to happen with that direction reaction rate constant? That will be increases always. So what is conclusion? Whenever you are going to increase temperature, my dear students, always reaction rate constant is going to increase. That's why in general cases, if irreversible reaction is there, every time we want high temperature because high temperature favorable, but make sure the temperature must be below than melting point or dissociation temperature, melting point of your chamber or container, or you can say a dissociation temperature of either reactant, you can say, or you can say product. So reaction should be at happen at high temperature. But if irreversible not is there, if reversible is there, then for reversible beta exothermic, definitely the favorable condition is low temperature. Just you had seen in conclusion that Ke is going to decrease where you're going to increase temperature for reversible exothermic reaction. For reversible exothermic reaction in हिंदी if you want to feel better, reversible exothermic reaction के लिए जब आप टेम्परेचर बढ़ाते हो तो Ke घट जाता है, और जब Ke घटेगा यार तो कन्वर्जन भी घट जाएगा. इक्विलिब्रियम कन्वर्जन जो आपको मिल रहा होगा, इक्विलिब्रियम कन्वर्जन इज नॉट 100%. इरिवर्सिबल रिएक्शन, इक्विलिब्रियम कन्वर्जन इज 100%. फॉर रिवर्सिबल द मैक्स कन्वर्जन दैट यू कैन रीच when complete forward reactant goes and backward product again converted into reactant, this when same, then you can say reaction reaches equilibrium. And definitely that time still reactant is there, that is the max conversion. And if reactant is still there, the 100% conversion is not there. That means the 100% conversion is not there. That's why you are writing XAE. That means conversion at the time of equilibrium. But if irreversible, equilibrium means what? When reaction is completed. So XA Max value in that case 100%. In fractional form you can say 1. Okay, please tell me everyone one more time, beta. Is it crystal clear? Can we proceed, my dear students? फटाफट बताते चलो, फटाफट everyone, beta. Please tell me immediately, immediately, immediately. Please tell me, beta. No doubts. All clear. Done. Can we proceed? Okay, sir. Now, how it is going to change with temperature? Very, very easy to see, beta. Just again focus on this beautiful relation. So, Arrhenius equation. Arrhenius equation. Arrhenius equation. Just you had seen this equation was k, small k, is equals to k naught e raised to power minus EA by RT. And my dear students, heat of reaction is a function of temperature. Maybe a function of temperature for your given case. Lambda, enthalpy of vaporization in Clausius and Clapeyron equation, is also a function of temperature. But when you are going to see beta this EA na, please my dear students, clearly write it is not a function of temperature always. I am writing, my dear students, always. Only one man who can change the value of EA. Can you tell me the name? If you change reaction, EA change. That's okay. But for same reaction, who is responsible if you are still seeing that activation energy changed? Please tell me. क्या बात है? Fantastic. Fantastic, beta. It's catalyst. Kiadas asks the conclusion is for reversible or irreversible. But this conclusion, even you can see for reversible one, how see? What I am saying you, ध्यान से देखेंगे यहाँ. If reversible reaction, so A is forming R. This is forward reaction rate constant. This is backward reaction rate constant. So my dear students, when you are going to increase temperature, Kf increases always. When we are going to increase temperature, Kb increases always. Is it crystal clear, beta? क्या दास बोलो, ये clear हो गया बेटा? Very good. Catalyst, fantastic. बोलो बेटा, आपको clear हो गया क्या दास? समझ गई हो? Are you able to understand this conclusion? Confirm, crystal clear, sir. Okay, okay, beta, fantastic. So now, see, this is our beautiful equation number 1. Now, same technique I am going to do in detailed manner, little bit in one half. We are in a little bit hurry because that topic is related directly with thermodynamic. But here also we will use that topic. How? I will tell you later, not in this lecture. I want to tell you. So just take logarithmic here. So you will get ln of k, and that becomes equals to ln of k naught e raised to power minus EA by RT. Now, you know log A, log B. Log AB can be written as log A plus log B. If you have something like ln AB, so you can write like ln A plus ln B. So my dear students, same thing I am going to do for right hand side. So ln of K is equals to ln of K naught and plus ln of e raised to power minus EA by RT. Now, one more rule. What is ln? Ln is nothing but log with base e. And if something is written like ln of a power b, then you can write this like b ln a. So here this can be written as minus EA by RT ln E. This one you can write like ln of K, and that becomes equals to ln of K naught and minus EA by RT into ln of E. And what is ln of E here? If ln of E you are writing here, then base E, and this is also E, then its value is 1. So further solving, my dear students, you can write this equation as ln of K. That becomes equals to ln of K naught and minus EA by RT. Okay, now see, this is your equation number 2. Now with the help of equation number 2, we want to write this equation for two different cases. Okay, see, if T is T1 beta, T is T1, that time reaction rate constant suppose is K1, and that time activation energy value is E1. If if T is T2, if T is T2, then K is K2 and EA that time is EA2. But, my dear students, just I told you now, activation energy is not a function of temperature, so no need to write, because for both cases EA will remain same, K will not same, but EA will remain same. EA आपका change नहीं होगा. So for this case, if you want to write this equation, then you can write like ln of K1 that equals to ln of this is constant, and see beta, this constant, this K is known as pre-exponential factor. This constant here in Arrhenius equation is known as pre-exponential factor. Pre-exponential factor. इसे क्या कहते हैं बेटा? This is known as pre-exponential factor because it is just used, you can see behind this exponential part. Sir, हमने सुना था we know it frequency factor. Don't worry, it is also known as frequency factor, but not for all cases. For which case it is known as frequency factor, I will tell you in my subsequent lectures, not in this lecture. Okay, so for this time, this k naught is just a constant, and here it is known as pre-exponential factor. Okay, so pre-exponential factor is also not a function of temperature here. So ln of k naught and minus ln of k naught minus EA. EA is not a function of temperature, so no EA1, no EA2, EA. And R is universal gas constant, that is also not a function of temperature. So EA upon R T1. Okay, this is your equation number 3. Beautiful equation number 3 you got here. Okay, now similarly here, you can write ln of K2 that equals to ln of K naught minus EA upon RT2. This is your equation number 4. I hope each and every student is crystal clear, because this time just I am doing general mathematics here. Just I am doing general mathematics. So now by equation 3 and 4, by equation 3 and 4, if you are going to subtract 3 minus 4, so here you can write 3 minus 4, you can write like this, 3 minus 4. What will we get? अभी 3 minus 4 करने पे क्या मिलेगा? Just see here. So ln of K1 minus ln of K2. Very good, very good. क्या था? K1 by K2 EA by R. Absolutely correct. बिल्कुल सही है बेटा. Fantastic. And equals to ln of K naught minus EA by RT1 and minus ln of K naught, this one, minus EA upon RT2. Okay, now when you are going to open bracket, my dear students, something going to cancel, that is ln of K naught. Further moving forward, it can be written as ln of A minus ln of B, that will can be written as ln of A by B. So it can be written as ln of K1 upon ln of K1 by K2, and that equals to EA by this minus positive. So I am writing this term first, EA by R in both sides. So I am taking EA by R common here. I am taking this EA by R common here. And here I am writing this one first. So 1 upon T2 minus 1 upon T1. So this is our final expression. This is our final expression. ये हमारा एक final expression हो गया है. And now see, in this expression, my dear students, EA and R will be given to you, and if T1 is there, T2 is there, K1 will be there, they will ask what is the value of K2, and maybe T1, T2, K1, K2 will be there, and they are asking about what is the value of activation energy of that given reaction. So in this reaction, any one unknown there, R is not unknown for us, R every time universal gas constant here. Okay, so if you want to see universal numerical, If you want to see a universal numerical, see universal numerical, universal numerical based upon this formula, one beautiful universal numerical, that is k1 k2 k1 k2 t1 t2 ea. So, my dear students, five types of numericals mainly form. Maybe K1 is missing, all data is given. Maybe K2 is missing, all data is missing, given. Maybe all data is given, and they are asking what should be the temperature at which the reaction rate constant going to convert it into K2. So maybe any one temperature may be unknown there, or maybe all things are given and EA is not there. So any one unknown. Mainly you can say one, two, three, four type of questions. So you can say any one unknown. Why I'm saying five types? Maybe lower temperature unknown, maybe higher temperature unknown, but both you can consider just like one case. So overall four cases. So any one unknown here, any one unknown here. Okay, is it crystal clear to all of you, my dear students? Is it crystal clear how to solve these type of numericals? Just one equation, one unknown. So very very easy to solve. Soon I will show you in my next lecture lots of new numericals along with lots of pyqs from this topic. Okay, is it crystal clear? Tell me everyone, beta, is it crystal clear? Now this equation is not completed yet. This equation is not completed yet, but lecture time is now I think finished. Just 1 or 2 minutes left here. Hmm? So I am giving that relation, complete relation today, and I will tell in my next lecture how I am writing this equation. Okay. So till now you know that this ln of k2 by k1 here, or k1 by k2 के फॉर्म में लिखा था ना, उसी फॉर्म में लिखा. k1 by k2 is here. This is ln of k1 by ln of k1 by k2. And one more thing, beta, how to remember this? If you are writing k1 by k2, then first t2 will come. So 1 by t2 minus 1 by t1. If you are writing ln of k2 by k1, then 1 by t1 minus 1 by t2. So this is little bit faster way to remember. ताकि examination, so that you can save time in examination, during examination. Okay, beta? Is it crystal clear to all of you, beta? Please, everyone, one more time, please tell me. फटाफट बोल दो सभी लोग, फटाक से बोल दो, everyone, please. Crystal clear? Okay, 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 beta. So the complete equation, I am going to give you ln of k1 by k2, and that can be written as E A by R. And here, my dear student, this is 1 upon T2 minus 1 upon T1. Now, in my next lecture, at the start of lecture, first, I will show you how I am going to write this, like ln of reaction rate of reaction at temperature 1 and temperature 2. How I am writing this like this ratio, or how I am going to write this like ln of t2 by t1 time. This is time. So how I am writing these things here, don't worry, I will tell you in detailed manner in my next lecture. Okay, अभी के लिए ये देख लो. And now I will tell you next lecture, and in next lecture you will see this is t2 by t1 or t1 by t2. ये t2 by t1 होगा या t1 by t2 होगा. Okay, so wait for next lecture, and hope beta everyone enjoyed today's lectures. बोलो सभी को मजा आया? All concepts are crystal clear बेटा. समय कब खत्म हो जाता पता ही नहीं चला यार. हैं? आज का लेक्चर 1.5 आवर का था. टुडेज लेक्चर इज ऑफ 1.5 आवर, एंड आई थिंक 1.5 आवर कंप्लीटेड. सो टाइम बहुत जल्दी ओवर हो जाता है. ओके, absolutely beta, every session will be interesting one. Okay, so for today, that's it. Enjoyed, sir? Thank you, sir. You're welcome, beta. Fantastic, mind-blowing, super. So today just you had completed this numerical. I think this numerical took too much time because conversion was also there. So समझाने में थोड़ा यहाँ लग रहा समय हमारा चला गया. Then you had seen just how Arrhenius equation developed. Then also you had seen about equilibrium reaction rate constant, and you had seen the Van Hoff equation, as well as you had seen Classes and Clapeyron equation. Classes and Clapeyron equation totally you will see in thermodynamic, but Van Hoff equation you will see in thermodynamic as well as here in this subject. Okay, that's why I had done some analysis about that Van Hoff equation. Soon I will discuss again that equation in some more detailed manner along with some numericals. Okay. Enjoyed, sir. Thank you, sir. Okay, beta. So take care. Love you all. A very, very happy good night to all of you. At the end of lecture, just I want to show you this slide one more time. If you want dream job rank 1 to 100, then beta revision is the key. I must do my Zen daily. I must do my Zen daily. I must do my Zen daily. I must do my Zen. I must do my Zen daily. So don't forget to revise your notes every day. In this manner, definitely you are going to join your dream job. Again, my dear students, if you want to prepare for GATE examination 2026 2027 beta, don't wait long. बहुत लंबा इंतजार मत करो. Just now start your subscription and see everything in a structured manner. Okay, and one-to-one guidance is also available for our online uh, uh, subscribers. Okay, so you can call me directly if you want to know any details about fees or other things. You can call me directly, or if you want to contact with our director Rajesh sir, and number is there. Okay, नीचे एक पट्टी चल रही होगी, number is there. Okay, so take care beta, all the best to all of you. Very very happy good night once again to all of you beta. Take care. I'm waiting till next 10 seconds. If no doubts from your side, then I will end the session. Activation energy with equilibrium constant. Equilibrium constant. No, but in equilibrium constant, you are going to show delta H heat of reaction. Okay. If you want to write, then you can write heat of reaction in terms of forward and backward activation energies, just as I shown you. Okay, beta Shian Mukherjee, is it crystal clear, beta? Sure. Okay, sir. Fantastic. So take care, beta.